Hello, this is the next video in a playlist that I'm calling Parameter Estimation, and we're going to look at unbiased estimates and mean squared error. And the bigger topic in this video is properties of the estimator. Okay, so let X be distributed with some distribution, and we're going to take a sample size of n. Let T be a statistic. We want to estimate some function of our unknown parameter, theta, with our statistic. And we assume that the theta lives in some parameter space omega. So how do we know if T is a good estimator, a best estimator, an optimal estimator for G of theta, what we want to estimate? Well, we have to develop some criteria to evaluate the different possible estimators for G of theta. Okay, now this concept actually I think is what makes a statistician a statistician. When we say X is distributed with some distribution F, we know what that means. That if we were to draw it, it looks, you can draw some sort of shape or curve and the probabilities under the estimate. But the statistic is also a random variable. And here's an example. If we take a sample size n from some distribution and calculate this statistic, it's a value. Now, if we throw away those 100 observations, or n observations, and take another sample size n and calculate this statistic, is it going to equal the statistic that we calculated from the other sample size n? And the answer is probably not. So this statistic is a random variable, and that concept is critical to be a statistician and to understand what we're developing from this point on in our playlist. So if our statistic T is a random variable, it has a distribution associated with it. And if it has a distribution associated with it, we can calculate the mean, we can calculate the variance, we can calculate the median of this random variable T, and etc. And that's what we're going to delve into now. So first let's define unbiased estimator, and that is if the average value of our test statistic is equal to G of theta, what we're trying to estimate, then T is unbiased for G of theta. And if an estimator is not unbiased, then it's biased. Now here's perhaps a silly graphical illustration of unbiased, and we're going to estimate the mean fish length and call it theta in a lake. So what we do is we catch a sample of size n fish, and then we somehow want to measure them, and then we're going to use that average fish length in our sample to estimate the population sample. But what if we forgot our tape measure and we only had a scale so we could weigh the fish? Okay, so this is what it would look like. If this is the average fish length and we caught a sample and we weighed it, and then from that weight we estimated its length to be some value. So we're using the fish weight to estimate the length, and we're going to get a distribution of our sample statistic something like this. Now what if we realize, wait a second, my shoe is about 12 inches long, it's 1 foot, so I'm going to just use my shoe to estimate the fish length. But really, my shoe was slightly less than 12 inches. So every time we measure a fish, it's a little bit shorter than what we really think it is. And so we're getting estimates like this. So the average is less. So there's some bias there, right? But the variability is going to be less in our estimator because we're using the exact same measurement every time to measure these fish. Where if we use weight, we could get a short, fat fish that we're, based on the weight, we think is actually longer than it is, right? Or another possibility is we actually have a tape measure and we measure every fish that we catch in our sample. And because, you know, and so when we calculate the average fish length, the distribution of that is going to be very close around the true fish length, right? So which way to calculate the average fish length is best? Well, of course it's this. But if you look at this method and this method are unbiased. The average estimate is going to equal theta, and here the average estimate is going to equal theta. But look at the variability associated with this. The possibility of being way off is much more than the possibility of having an estimate that's very far from the true average fish length. So somehow we have to factor in or bring in the variability of our estimate. And here, while the variance is sort of low, it's a biased estimate. And so somehow we have to consider the variability in our estimator as well as the bias. So these are unbiased, but this has less variability in it. Now this has less variability, but it's biased. So which one's better? Well, I don't know. So somehow we need to look at this distance from the distribution to our unknown parameter. Well, and when we do that, and then we look at the average of those distances, then we can develop something that's called a mean squared error. And it's represented MSE, so it involves our test statistic, the unknown parameter, theta, and it's calculated like this. It's the average, or the expected value of our test statistic, minus the value we want to estimate. We're squaring that distance and taking the average. So it's the average squared error, the mean square error. Now, sometimes it's called risk, and when we jump into what's called decision theoretic estimates, we'll call it risk instead of the mean squared error. But really, it's 100% the same. So I mentioned a second ago that there's bias, and the bias, so if we look at this piece here first, the bias of our estimate, T, is the average value of T minus what we're trying to estimate. So this difference is bias. And some people represent it as a B, and then our statistic and our parameter, and some people write out bias. Okay, and unfortunately I mix them up, and so we'll use both notations. If I'm running out of paper, sometimes I'll just put B's to save space. Otherwise I try to write bias. Now, since T is a random variable itself, we can calculate the variance associated with it. And actually, when you look at statistical reports and it talks about a standard error, that's what it's actually referencing. It's the standard deviation associated with our statistic. That's called standard error. So common is standard error of the mean. So the variance of our estimate is variance of our statistic is the average squared distance of our statistic minus its mean. Okay, so note that when T is unbiased for G, then the variance is actually the mean squared error, right? So if this is unbiased, then we put G of theta here, and then it is actually equal to the mean squared error. So let's prove that. So the variance by definition is this, but if this is unbiased for G of theta, we put it in, but this is actually the definition of mean squared error. So unbiased estimates have mean squared error equal to the variance. Now, the mean squared error can be shown to be the variance of our estimator plus the squared bias, right? And if it's unbiased, meaning the bias is 0, then the mean squared error equals the variance. So let's prove this. So this is the mean squared error, and then here we add expected value of T and subtract the expected value of T. And then now we're going to square this, but we're going to think of it as a unit. So it's this squared times, this squared, and then it's this times that, so you get 2 times this quantity here. Now, if we look at this is what we were calling variance. this is the bias. It's the average minus the value. When you square it, you can switch those around, and that's the bias squared. And then when we take this expected value into this is a constant, this is a constant, that's a constant. So this is not a constant, this is a constant. So you bring the expected value in here, you get the expected value of t minus the expected value of t. So this is 0. So this is true, and that's what we wanted to show. Now, we're going to introduce a concept of uniformly minimum variance unbiased estimator, UMVUE. And some people leave off the E and then they always say estimator. So it's a UMVUE estimator. But I always like to say UMVUE. Now, let's let T be an unbiased estimator for G of theta. So T is a UMVUE, so it's a uniformly minimum variance unbiased, if it has the smallest variance in the class of unbiased estimators for G of theta. That is, the variance associated with our statistic is less than or equal to the variance of any other unbiased statistic that we choose, for any other unbiased delta, and this is for all theta in the parameter space. Then our statistic T of theta is called a UMVUE. Okay, well, that's all I have for today. In the next upcoming videos, we're going to explore a lot of these ideas, provide examples, and etc. So I hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.